Okay, so welcome back to the Zelda tutorial series. Um, I'm kind of hesitant going forward about this tutorial series only because I've read and heard that Nintendo has some pretty strict copyright infringement type activities that they like to you know enforce, and I really hate to put in all these hours into a full working and expanded original Legend of Zelda, um, only to have the whole project get hit with a cease and desist, and I have to pull all videos. So I'm kind of hesitant, but I'm gonna continue on with what I've already at least drawn out, and we'll go from there. I think my videos are getting such low attention that it's not really going to draw any kind of attention from Nintendo. But you never know. Even very small products or projects rather have been hit with cease and desist. People like their IP, and they don't like it to be misused or used on any projects, even if there is no monetary gain there. So we're kind of skirting a fine line with this educational purposes type use. We'll see. But I'll continue on. But so right now, what we're looking at is what your code should look after this probably a pretty long video. Okay. And it might be bug ridden, and that we'll have to eventually go through and look at it line by line to figure out what I may have missed in making our current code, which is basically a static enemy, into an enemy that is able to choose a route throughout the map and move in that direction. Okay. And so, I actually had this lesson all ready to go months ago. In fact, it was over a month ago that I had put everything into code from start to finish for this video and some future videos. And I just never got around to them. Time hits you, and so without further digression there, this is our final project here, right here, for this lesson. Okay, and so how are we going to get there? All right, so let's go ahead and look at what your starter code looks like. Okay, so this is the starter code. And I know this says lesson 17 up here, just disregard that. And what we want to do is we want to have a path chosen for our enemy. Okay? And so let's see here. What we want to do is we need to go down to draw objects. Okay? And inside draw objects, we have our if is enemy. Okay, and so what we want to do is, and adding this or programming it after I've already programmed it before, there's going to be code in here that you're going to be like, I wonder what he's doing there, but I will try my best to explain this as we're going through. Originally, I had a dynamic solution where it was basically a depth first search. Okay, and so and I was just grabbing that first path, and I was having some pretty in retrospect, it was not a serious issue, but I was having issues with the code, and I decided to re-roll the pathfinding, And what we're doing right now is, I believe it's just an implementation of Astar, okay? And I looked at some pseudocode and I just programmed it from there, okay? Or actually, I looked at some, I believe it was Python code, and I just turned it into JavaScript. What we're going to do here is, what we want to do is we want to see if there is an enemy path, okay? And so inside of game objects, we may have to go look at that real quick, all right? Because if the enemy is going to have a path, let's see here, game objects, and what I need to do is I need to open up our maps file, and we'll edit that in Notepad++. And so here in lesson 15, I'm not sure if I just included this into what you currently have, but basically this is what we are looking for. So right now, all enemies start with an empty enemy path, and this is just their little jaunt through their current map until they get to an endpoint. Okay, and so right now it's empty, and so we want to make that full. Okay, we want to fill that path up. And so how are we going to do that? Well, we're going to say if game objects at I dot enemy path is equal to null, or game objects at I dot enemy path dot length is equal to 0. Okay, so we're going to see if first of all, if it's not assigned yet, okay, or if it is 0. Okay, and so this is really from my previous implementation, and I just never took it out, and that's fine. So this is, as we go through our path, we're going to get rid of the location that we've made to last. Okay, and so every time we get to a new square or tile that is part of our path, once we get there, we take it out of our path and we look at the next tile that we need to move to. And so we're constantly popping them off until we get to our last tile. And once we get to our last tile, we have popped off that tile, and now our enemy path dot length is equal to 0. So what do we want to do if our enemy path is equal to 0? Well, what we want to do is we want to get a new coordinate, okay? And so we're just going to go ahead and get our current coordinate, our current row, and our current column, because our new coordinates need to be reachable from our current coordinates, okay? And so we're just going to get our current coordinates. So we're going to say let current row, and then we're going to say equal math.floor game objects at I dot y divided by 16. Okay, and our column is much the same, so I'm just going to say copy that, and here instead of row we're going to say col, and this is our x value. Okay, and then we're going to make a call to a new function that we don't have yet, and we're just going to say get new coordinates, and then we're going to say cur row, cur call, and this I is our current enemy or game object index. Okay, and so we're just going to pass that along. Okay, so we're going to come back to this, but right now, since we're already here, we're going to go ahead and define this this method right here. Okay, so we're going to come down here, and I am just going to make sure I follow my guide as quickly, or as accurately as possible, because I know y'all get tired of me here, or tired of hearing this, but I'm tired. It is 11:26, and I did not sleep well last night, but there has been a lot of interest in this video, and I've been meaning to get this out for quite a while, and I do have some extra time tonight. So we're just going to say function get new coordinates, and we're going to take in that current row, current column, and then our index. So this is what we want. And so what we're going to do is we're going to get a random row and a random call. Okay, so we're going to say let rand row equal math.floor math.random times 11 plus 4. Okay. So what we're doing here is we are getting the row within our map, and remember the top rows are, this is going to give us a value of 0 to 11, exclusive of 11, and so we want to add 4 to that, and we're going to go what this random row is going to eventually give us is a value of 4 to 14. Okay, and so that's going to give us the game rows. That's not part of the HUD. Okay, and then we're going to go ahead and do our random call. So rand call is going to be 15, and we're not going to add anything to it because all the columns are let's see here, game map, and then we're going to say rand row rand call is not equal to 2. Okay, now here's the thing. So what we're doing here is we're saying, well, if it doesn't equal to 2, it's not a square or a tile that we can occupy or traverse over. So we're going to get a new random row and a random column. But there's we're missing a big piece of this puzzle, in that there are many other squares that we can occupy that are not 2, and eventually this will be a variable, an array. Okay, and we'll just traverse that array to see if we can go to any of these values, but 2 is what we're sticking with because that's what we currently have, and we'll come back to that later on and fix that so that the monsters can go to any good square, traversable square. And then so game objects at index, this is what we passed in, dot enemy path is equal to a star, and this is our path finding algorithm right here. Okay, so our a star, and then what we're going to pass in is a new position, and I'll have to see if we actually have position within our code. Probably not. So we're going to say current row, current call, and also another new position. And actually, I'm just copy this. And this is going to be rand row. And rand column. Okay, so this is going to get us a new path. So that's what we're doing here. And we also have to pass in the game map. Okay, so that's that. So let's go ahead and do this. And so it is possible that Astar does not give us back a path. Okay, it did not find a path. It looked for every possible way to get to this random row and random column, and it did not find a path. So what are we going to do? Well, we're going to say while game objects at index dot length is equal to 0. So while it still does not have an enemy path, we are going to get this again. And so that's fine. And then we're also going to so rand row, yeah, that looks good. And then we're going to call this function again. Okay. And eventually it's going to give us a new path. Okay. And so we're done with getting new coordinates. Okay, so that's pretty easy part. We're just getting the new coordinates and then calling this other function. Okay, but we've introduced a new object. Okay, and that's this position. And so we're going to just go ahead and define that real quick. So, and it's going to take in a row and a column. And we're just going to say this dot r is equal to row. This dot call is equal to, or this dot c is equal to call. Okay. And then, so that's all we need here. But we have this idea. So we need to, now that we have gotten to this point, we need to come back and implement this function. Okay. But within this function, there's like a type of object that we need for this function. Okay, and that's going to be called a node. Okay, and so what we're going to do is we're just going to say function node, and what it's going to take in is a parent and a position. Okay. And so what we're going to do here is we're going to say this dot parent is equal to parent this dot position and this dot g is equal to O, this dot A or 0, this dot H is equal to 0, and this dot F is equal to 0. Okay, and so what we have now is these values G, H, and F, which I've set to 0. And so what these really are is G is the cost that cost or distance from the start node to our current node. And so as we go through this algorithm, we're going to go from the start node to the next node to the next node to the next node. And we're going to get that value from the start to whatever our current node is. And then this h value is going to be, this is a set value. This is like a definite value. It definitely costs, 4 whatever to get from start to this current node. Okay, this is something that you can definitely calculate. This is going to be an estimation. Okay, h is the estimated cost from our current node to the final node, and basically what you want to happen is to have this as close to the real value as possible without going over. Once you overestimate the cost from current node to destination node, you start to you may not have optimal results, or it may not even find a value that, or actually, it'll probably still find the value, but it may not do it in an optimal manner. Okay, and this F is basically just G and H combined. Okay, this is the total cost of actual plus estimated from start to finish for that particular node. Okay, and so that's all these values are. And as we go through the algorithm, this Astar algorithm, we're going to update each of these for each node that we assess. Okay, and then so what we're going to do now is we are going to look at our Astar algorithm. Okay, now in case you're looking at or trying to figure out where I got the pseudocode, well, it's actually real code, but I think it's in Python or whatever. You can go ahead and look at this this little article, basically describing this algorithm, and so I basically implemented this version of Astar. But there are many ways that you could implement it. Really, Astar is basically these values, and then how we estimate the cost, and then choosing the path from that point. Okay, and you can implement it using various data structures, and so yeah, that's basically it. So this just so happened to be the easiest one to follow. Although I have done Astar using other projects, I don't memorize the algorithm by any means. I'm not like a full-time video game programmer or anything like that. So I just looked up the Astar algorithm, and that returned. But anyways, let's go ahead and do this. So we're going to define this function, and this function we're going to have a name, Astar, and it's going to pass in 3 parameters: start, end, and maze. Okay, and we could have called that map or whatever. Okay, so at each position we're going to have a start node, or actually no, this is as we enter. When I said at each position, because usually I'm thinking of Astar as a recursive algorithm, where we keep on calling Astar until it finds a result, and then we pass it back. But this implementation of it is not recursive at all. It just uses loops to get to the final answer. So, either way is just fine. So we're going to say that the start node is going to be equal to a new node, and the first value of this start node is going to be null, and the second one is going to be start. Okay, so this is the start value that we are coming from. This is our current position on the map as an enemy. And so that this is going to fit into our start node, and then our this parent. See, if we remember back here from our node, this is the parent. There is no parent for the start node. That is the parent node for everything that follows. Okay. And then what we're going to do is we're going to say end node is equal to a new node, and it is going to be null for now. It's going to be null, and it is going to go to the end. That's its position, is the end of the whatever. And so we're going to have an open list. And if you want to read up on the open list versus closed list and so forth, feel free to go to this article. I think they do a pretty decent job of explaining it. So what the open list is all the nodes that you can get to from your current position. And then closed nodes are ones that you have already assessed. Okay. So let's go ahead and what we're going to do is we're going to look at what we're going to do is we're actually going to add our first node to our open list. Okay, and our first node is going to be our start node. Okay, so we're just going to say open list dot push, and we're just going to add that start node. Okay, and then what we're going to do is we're going to say while open list dot length.
You can ask me to help plan your day, communicate, get mobile info, or play media. To learn.
It's my phone. Sorry about that. We are going to say while open list is greater than 0. So while we have moves available or positions that we can assess available, we're going to say current node is going to be equal to open list at 0, and our current index is equal to 0. All right, and what we're going to do is we're going to look through all the values within our open list to see which one has the lowest F value. Okay, so why do we want the lowest F value? Because we want to find the shortest path from point A to point B, and this F value is the estimated, it's the real and estimated cost to get from point A to point B, and we want the lowest cost. Okay, and so what we're checking is, if there's another node in our open list that has a lower F cost. Okay, so we're just going to iterate through that list. So we're going to say for I is equal to 0 while I is less than open list dot length I plus plus, and we're just going to say if okay, so if we find one that has a better f value, we're going to say current node is equal to open list at I, and the current index is equal to I. Okay, so we found one that has a potentially lower cost. And I say potentially because we're estimating the h, okay? So that's just our estimation. And that estimation is usually based on some Euclidean distance, which we don't know if there's obstacles in between. So it's an estimation, not knowing if there are obstacles. So right now, this may look like it has a lower cost, but it may not have a real lower cost. And so what we want to do is if we go through and we get this new node, what we want to do is we want to get rid of this new node from our open list. Okay, and so we're just going to say open list dot splice, and we're going to say current index to 1, so just past it, and then we're going to say close list dot push, and then we're just going to take our current node. So we add it to our closed list. And so what we're going to do now is we're going to excuse me, we are going to check to see if we are currently at the end position. So we're going to say if current node dot position dot r is equal to end node dot position dot r, and c is equal to end so if this is the case, we want to return the current path. Okay, we have found our target. Okay, it is one and the same with the current node we're on. And so what we want to do is define some parameters and eventually return a path. Okay, and so what we're going to do is we're going to say let path equal to this empty array. Let current equal current node, and while current is not equal to null, and so basically we are going to use the nodes to find its parent. Okay, so if I move from one square and I'm moving to the second square, number 2, my parent, the parent of 2, is going to be 1. Okay, and then if I move to a new square, new tile, to 3, then 3's parent is going to become 2. So basically, if I have the end node, okay, if I have the end node, all I have to do is keep on calling the parent of this node and then set this node equal to the current node and call its parent, and so forth and so on. And I can go all the way back to the start node from the finish node, and that basically defines our path. All right, and so that's all we're doing here. We're starting with our current node, which is our end node. We have ended up here. Okay, it equals our end node, and we are saying while the current one is not equal to null, we want to do something. Okay, well, what do we want to do? Well, we want to push it to the path. And then we want to set our current one to the parent. Okay, dot parent. And so we're just doing exactly as I had just said. And what we want to do now is we want to return that path. And that's it. Okay. So that's nice. This ends our while loop. But we're not done. Okay. This is just our are we finished? Okay. If we're not finished, we need to do a whole lot more. Okay. So we're going to create an array called children, and we are also going to create an array called positions. Okay. But we're going to define our positions. So these positions are positions that we could end up, they're basically the adjacent positions to our current tile. And in Zelda, we can only move up, down, left, and right. And so our positions are going to reflect that movement to those new tiles. And so if we are moving to the row column, if we're moving to the left, we're going to have a new position of our current position plus this new position. Okay, so plus -1, we're subtracting the 1, and we're moving to the left. If we're moving to the right, basically the same thing, except we're going to get rid of this. This is going to be a and really it didn't matter what order we put these in, and this would just be a -1. Okay, and so that's our array of positions that we can move to. Now if you are creating another game in which there is like hexagons, so you can move in 6 directions instead of 4, well you could just update this, and you can still use Astar in that situation as well. And so what we're going to do is we are going to say for that I is equal to 0, I is less than positions dot length. I plus, and we are going to get our node position. Okay, so our node position is equal to a new position, and it's going to be our current node dot position dot r plus the new position that we want to get to. So from this array right here, so positions at I dot r, and then I'm just going to copy this, save us a little time. the column as well. So column, done. All right. What we want to do now is if the node position.r is greater than maze, well, I'll just maze.length minus 1. So if it's greater than the maximum length of our maze, or node position.r is less than 0, okay, it's out of bounds. It's and so that's really what we're doing, is defining the bounds of our node position, our potential node that we're going to travel to, okay? And we want to travel within the bounds of the map, and so we're checking to see if these are out of the bounds. And I'll go ahead and put these in parentheses as well. It doesn't really affect it. And then, so here we're going to say, actually, it does not affect it, so I'll just do this. So we'll say node position dot c is greater than, and I'm going to move this to the next line because we'll eventually get some cutoff, I think, possibly. And so node positions dot c is greater than maze at 0 dot length minus 1, or node position dot c is less than 0. Okay, so this is our if statement. So if this is the case, we don't want to keep this position, okay? The position's worthless to us, and we're just going to continue in this loop looking at new positions, okay? The next position. And then we're going to say if, and so this is our next condition, okay? So these are all invalid nodes that we want to travel to, and currently anything that's not a 2 is also an invalid node. So we're just going to say maze at node.position.r, node.position.c is not equal to 2. Okay, this makes it invalid as well. And if that's the case, we'll just continue there as well. Now we could have just made this a compound, like a compound if statement, and just added another condition here. But this, it's different than finding this, and so I just like to, separate the two. And so if we didn't continue, well, we have this node is something that we care about. Okay, and so right now we don't have a node per se. We have a position for the node, so we're just going to create that node real quick. And so we're just going to say let new node equal a new node, and so we're going to say current node and node position. Okay, and we're going to say children dot push new node. All right, and so that ends our for loop. And so what we want to do now is we want to evaluate all the children we just found, okay, to see if we can push them to our open list. All right. And so here we're just going to say for let I equal 0 while I is less than children, dot length I plus plus. And we have another for loop, an inner for loop, and we're going to say for let j equal 0 while j is less than closed list dot length j plus plus. And let me just see something here, just making sure. J plus plus okay, and so we're going to say if children at I dot position dot R is equal to closed list at J dot position dot R, and I'm just going to go ahead and copy this because we're just going to check the column and row of each children to see if it's already in our closed list. If it's already in our closed list, we don't want to worry about it because we've already evaluated that from a closer node, okay? And so any node that looks at it after it's added to the closed list is a node that was farther away from the original node that made it to that child. And so we're just going to completely ignore that child, if that makes sense. And so we're just going to say continue here. And then what we're going to do is we're going to evaluate our values. Okay, so these are the things that we have not touched yet, and those are the G, H, and F values. So we have this child node, and what we want to do is evaluate its position, or its estimated and real values. Okay, so we're just going to say children at I dot G is equal to current node dot G plus 1. So our current node is the one that we're standing on, and we are looking at the tiles around us. And if we move to a new tile, we are adding 1 to our path cost. Okay, so that's all we're doing, and it's a real value. We are certainly adding 1. It's not estimated. It took us another step to get to the end. And then what we're going to do is we're going to say children dot H, children at I dot H is equal to. And so here, what we want to do is we just want to take the estimated cost using point, just like the distance between 2 points. Okay, and so that just looks like this. So we're going to say children at I dot position dot R, and we're trying to get to the end position, so we'll say end node dot position dot R times children at I dot position dot R minus end node dot position dot R, and then we're going to add so basically the same thing right here, and all the C values. So C, 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 C. Okay, so that's the H value. And then what the F value is just children at I dot F and we're just going to say it's equal to G and H. Okay, so it's this. So you may be thinking, well, we have this G value and this H value, and why couldn't we just, at the time that we want to find F within this, within our code, okay? Well, what should we do? Okay, why do we need this if it's just a simple operation of this plus this? Well, the thing is we may be comparing f, this children at I.f, versus many different nodes, and it's better just to store the single computation once and just call this, because then that becomes an O, just a single operation. It's a lookup. But when we're doing this, what we have to do is we have to look up, if we're trying to find f on the fly by just adding G and H, well, we have to look up this, then look up this, and then add the two. Okay, so it's many more operations than we need. So whenever you can take an operation that will be looked at multiple times and cache it in some way, you want to do that. Okay, it's just it makes it a little bit less CPU intensive. And then what we're going to do is, once we have these values, we're just going to say for let j equal to 0 while j is less than open list dot length j plus plus, and we're going to check if it is already in the open list. So the child that we have created, we're going to check to see if this child is on the open list, and if it is, we're just going to continue. We're not going to add it. And so my dog's going crazy. Give me 1 second. I'm just going to push pause real quick, and then I will continue. Okay, so what we want to do is check to see if it's on the open list. Okay, and so we're just going to say basically this same thing right here. Okay, I'm just going to copy this if statement, paste it here, and close, change open or close to open. Okay, so we want to see if it's on, if it's the same position, but also we have one other thing to check. We're just going to check to see if the G values match. Okay, so children at I.G, or they don't match rather. Okay, so if the child has gotten to this node and its G value is greater than the value already on the open list, we just want to skip it. Okay, it doesn't interest us because it's a a path that took longer to get to. Okay, and what we're going to do at this end is we're just going to push that child onto the open list that we need to evaluate at that point. And eventually we'll get to a point where there is no children that we can put onto this open list because either A, we have reached the end position, or I'm sorry, this doesn't reach the end position, but one of these does, or you know, the children are just less efficient, okay, as far as like the cost. And so what we eventually get to is we have nothing on the open list. And when we have nothing on the open list, well, you know, if this condition right here, if this condition did not fire off, okay, and we have nothing on the open list, then guess what? A star is not going to return a value, okay? It's not going to return that path, okay? So this is the only condition that returns a path, and if it was never met, A star ends, but a path is not returned. And so that's what we're doing up here. We are saying, well, if the path returned was still a length 0, meaning that there were no positions within that array, let's get a new path, okay? And so, yeah. All right. And so that ends the A star implementation, but we're not quite done. We need to go back up to our draw game objects and go back to our enemies. Okay? And so give me 1 second. All right, so roughly line 890-ish. Okay. So we have gotten the new coordinates, and we followed that get new coordinates to the A star implementation. And then so within this tutorial, we're also going to figure out if they need to shoot. And so usually they need to shoot at certain positions once they get to a new tile. Once they get to a new tile, they will determine if they need to shoot. Okay, so that's part of this path planning process. They're going to go to new tiles, and we need to account for that. So when they get to that new tile, they're either going to need to shoot, so it needs to shoot, or they're not going to need to shoot. And if they're not going to need to shoot, well, hey, they are probably going to go to the next position in their array. So, but if they need to shoot, we need to do something here, okay? So we might as well go ahead and take care of this. Not save it for the next tutorial. We already have the if statement, so we should include the logic. Okay, so if it needs to shoot, what we're going to do is so we're going to increase the shoot counter, okay? If game objects at i.shootCounter. So the idea behind this is they sit for a while before they shoot. Okay. So if it is equal to a 100, what we want to do is we want to add a new game object. And then we're just going to say go.x is equal to our game objects at I. So this is our parent, which is the enemy that is currently shooting. So game objects at I.x. And so you may be wondering, what is this new object? Well, it is the thing that they're going to shoot, okay? And so we need the x and y for the start of that object. So that's our x and y. And then we need to figure out what is the speed of our object, okay? So we're going to say if game objects at I dot direction is equal to down. Go dot y speed is equal to 2. Okay, so now that we have that, I'm just going to copy and paste. So if this is up, this is a -2. All right, and then I'm just going to copy these two. I just copy one, but so this is going to be left or right, and then this is going to be x speed, and then left. Ooh, this is not -22. That'd be really fast. And then this is going to be our x speed as well. So we have y speed, +2, -2, x speed, +2, -2. All right. And so we have a few, what we want to do is, so there are 2 types of projectiles that I have currently defined in my final game, or the current progress of the final game. And so I'm not quite sure if we have these, and if we do not, we will add them to our game object. So we're just going to say dot water projectile is equal to false. Go dot is portal is equal to false. Go dot is rupee, you guessed it, it's equal to false. And then go dot rock projectile is equal to true. So I will say that it's really good to be consistent with your naming, and I'm not doing a good job of modeling that. For instance, I say is portal and is rupee, but then I come back and I say water projectile, rock projectile. What I should be doing is saying is water projectile and is rock projectile, just to be consistent with that, the naming, so that people will immediately know what it is. But I have not been consistent. But in your future projects, you probably want to be consistent. It just helps with future readability for yourself and for others. Okay, so we're going to push that to the game objects, and it's a new projectile. All right, and then we're at this point we have shot the rock, and what we do is we sit in our current position as an enemy for a little bit more time, and we're going to say if game objects at I dot shoot counter is greater than 130. What we're going to do is we're just going to reset that stuff. We're just going to say game objects at I dot needs to shoot is equal to false. So we reset that. Okay. And so that ends the shooting. Okay, so maybe we do not draw this today, this rock projectile, although I think it'd be cool if we did. We are already hitting an hour for this one, and we still have a little bit more to go. Okay, so what we want to do now is we want to define what happens with this else. Okay. And so this else statement is basically the end of what we have to do today. And then we have to figure out if we have any bugs, if there are variables that I missed. Okay, so if game objects at I dot enemy path at game objects at I dot enemy path dot length -1 is not equal to null. Okay, so I am figuring out if the current game object, the current position within our enemy path, if it is equal to null. Okay, if it is not equal to null. If it is equal to null, then all this is, it doesn't matter. We're not going to do this if statement. Okay, and game objects at I dot next x is equal to game objects at I dot x. And so basically what we're doing is we're just seeing if the current next x is equal to our current x. If that is the case, we have made it to the next tile within our enemy path. Okay, so that's what we're checking here. We're checking first, do we have a next path to go to, a next tile to go to? And if so, we want to make sure that we have made it to the enemy path. And so if that is true, I'm just going to change this to a y and this to a y. If that is true, we need to change our next x. So we have made it, this next x is equal to our current x, so we need a new next x. Okay? Our new next x is going to come from that enemy path. Okay? So we're going to say game objects at I dot next x is equal to game objects, this whole thing, dot c times 16. Okay. And so what we're going to do is copy this, and we're going to get our y position. And so it's very similar. So y, 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 and then this is our row. Okay. And then what we're going to do is we're going to get rid of that node or position from our enemy path. So we're going to say game objects at I dot enemy path dot splice. And what are we going to splice? Well, we're going to splice the game objects at I dot enemy path dot length -1 to one position over. And I see that I made a typo right there. Okay, and so that gets rid of that. And what we want to do is when we make it to a new tile, we want to have a chance of firing. Okay, so what we're going to do is we're going to say let chance equal to math.floor math.random times 60 if chance is equal to 0 So basically we have a 1 in 60 chance of needing to shoot. Now, you could change this. If you want them to shoot every single time jeez. I hate when these clear all notifications. For some reason, Windows likes to save all my notifications until I don't want them to pop up, and they just, keep on popping up. But so you could change this. Right now, I just wanted a 1 in 60 chance. But if you want to say if chance is less than 60, okay, that means that this will happen every single time. Okay, and what we're going to do is we're going to say game objects at I dot needs to shoot is equal to true. Now this would be horrible for performance and for difficulty of the game. So this is probably not what you want to do. And so I'm just going to go ahead and take it back. Although it might be fun to see exactly what it does later on. But yeah, we'll keep it as is. Maybe we could have like an ultimate mode for difficulty and see what happens. Okay, so let's see if there's anything else down here that we might need to change. And so we have, do we have a needs to bounce? So we do have a needs to bounce right here. And we have something a little bit extra left. So we have not defined movement within our path. Okay, so basically we have said, well, hey, if we've gotten to the end of our path or the next position within our path, pop that or splice that position and go to the next position. But we've never actually updated the X's and Y's for Link to progress through the game. Okay, and so what we want to do now is exactly that. We're going to say down here under this, if game objects at I dot needs bounce. Okay, just go ahead and click right there and go to the end of that, and we're just going to say else if, because there's actually even more logic that we'll need to follow from there. And so this is going to be an else if. We're going to say if game objects at I dot enemy path dot length is not equal to 0. If it's not equal to 0, it means that we have a position that we have not made it to. Okay, we are somewhere along our path, but we are not there yet. So we're going to say if game objects at I dot x is not equal to game objects at I dot next x, so if game objects at I dot x, our current x, is not equal to the x that we want to get to, what do we do? Do we just add 2 and get to the next x? Well, we need to define, or we need to do figure out if the next x is less than our current x or greater than our current x. And so that's basically all we're going to do here. We're going to say if game objects at I dot next x is greater than our current x. And I'm just going to copy that. Oops. Not what I meant to do. And if that's the case, we need to just say if game objects at I dot counter mod game objects at I dot speed is equal to 0. Okay, so if it's equal to 0, we're just going to say game objects at I. Great thing is all this logic that we're currently typing out, we are going to be able to just copy and paste in a second. We're going to plus equals 2 there. Okay, and then we're going to give it its direction. We're just going to say game objects at I dot direction is equal to right. Okay, and so I'm going to go ahead and just copy this if statement, paste it, and we'll just say else if. It doesn't really matter here. And then so if this is less than, so change this greater than to a less than, we are just going to say -2, and it is coming from the direction of left. Okay, so what I'm going to do is I'm going to copy this whole thing. We're going to make it an else if, and so this is the so this is our if statement. This is the else if that we just pasted in. Okay, and so now what we're going to do is we're going to check the y's. Okay, so here we're just going to say dot y next y and this is going to go down. And this is going to go up. Okay, and then so we have one other statement that we're going to have here, and it's just going to be an else if game objects at I dot enemy path dot length is equal to 1. We are going to, so basically we want to just get rid of the current path and just get a next x and next y. Basically set this x to our next x. Okay, which doesn't make a whole lot of sense now that I'm saying it, but just in case it affects things. Because our current x, if it does equal 1, our current x should equal our next x. But I'm just going to do it just in case. I'm going to have to track down the bug just because I decided to change something at the last minute. Okay, so this is interesting because we have come to the end of our lesson or tutorial or whatever we want to call this thing. But I think I've missed some things from game objects, but we're just going to run it and see. Let's inspect. I think I'm having some node positions is not defined on 1241. Okay. So 1241. If node, okay. So just there was an S there on node position. Looks like another error. Okay, node is not defined on 1245. Let's go ahead and look at that. Node. Oh, node dot position. So node position. Node position. Okay. I knew this was going to happen, so we're just tracking down these new node is not defined on 1250. And so this is, again, consistency. I was not consistent with, usually you'll want to either use like an underscore to separate a new word within a variable name, or you'll just want to use camel case. And I'm so used to using camel case that sometimes when I'm looking at some pseudocode or whatever, I'm trying to follow it pretty closely, and I'm using the underscores, I go ahead and sneak this the camel case in as well. So it's like basically I'm trying to do both at the same time. So that's new node right there. Okay. And he's shooting, and he's finding his new path. He's shooting, and he is on his way. All right. So that looks good. That looks good. Okay, well, I think we've come to the end of this tutorial. So this was not as long as I thought it would be. In the next tutorial, what I would like to do is go ahead and fix some things that we need to look at that I'm seeing in this tutorial. And one of them is this right here. So we go into the next screen and we are booted over 16 pixels out of place, and so our back should be just right here, and so that's something that I would like to look at. That's an easy fix that I don't want to hit right now. The next thing is actually firing that projectile, and so that's going to be that's going to make this look a whole lot more complete and fun. And then from there, the sky's the limit. I think my current implementation has a full working HUD, especially when you hit start or whatever, and the HUD comes down and it shows you the rest of the HUD. Your selectable items and stuff like that. I think that might be cool as a future lesson. And so yeah, lots of cool things that we can do from this point on. But this pathfinding is so much fun to do. It adds just that element to the game that it's actually alive. Your creation is alive. And so this only works for certain enemies. There are other enemies that we're going to have to come up with different ways of getting them to move around the world. Spiders, for instance. So yeah. But for now, this is looking good. I hope to see you in the next tutorial. Sorry that this tutorial was so far from the last one as far as time goes, but sometimes patience pays off and you get something that looks pretty cool. I will see you in the next one that will hopefully come pretty shortly.